Hello everybody, welcome to another video lesson. Today we're going over vector projections. Our objective for today will be to find the projection of one vector onto another. So let's hop right into it. We only have one concept slide today. Okay, so our vector projections, thinking of our vector components, right? We have horizontal and vertical components. However, sometimes it is going to be really helpful for us to set those components not just in the horizontal and vertical axes. So I wouldn't just say along the x-axis and the positive y-axis all the time, but it might be helpful to set our components parallel to another vector. Okay, case in point here, we've got vector A and B. We've got some angle in between them, and I'm going to set our components for A to where one of them is parallel with vector B here, right? So I'm naming these C1 and C2 for our components here. And C1, we would call this the projection of A onto B. The projection of A onto B. Okay, that's how we would pronounce this right here. Okay, and that's this C1, the first component of vector A here. Okay, so now, since we have this right triangle, we know how to evaluate the cosine of this angle. What would the cosine be? Well, that's going to be the magnitude of C1 over the magnitude of our original vector A. Okay, magnitude of C1 over A. Now, if I were to multiply both sides by the magnitude of A times the magnitude of B, so the magnitude of both of our original vectors, okay, our magnitudes of A on the right-hand side would cancel out. However, remember here we have cosine of theta is equal to the dot product, okay, A dot B over magnitude of A times magnitude of B. Now, if we go ahead and solve this for the dot product, we get exactly what we have here on the left-hand side of our equation. So we are going to substitute in the dot product of A and B, or A dot B, on this left-hand side, right? And all we have left on the right-hand side is the magnitudes of C1 and B multiplied together. And if we go ahead and solve this for C1, we are going to get A dot B over the magnitude of B, okay? Now, I am going to say that the projection of A onto B, that is equal to the magnitude of C1, okay, the magnitude of C1, this component right here, the magnitude of this component, times vector Bx. Now don't get confused because this says x here. All I'm saying is that B is going to be the unit vector of B, okay? The unit vector of B in the direction of B, okay? And we figure that out by saying the vector B divided by the magnitude of B. Okay, we saw that in a previous lesson. Okay, so Bx is actually just a unit vector in the direction of B. Okay, not necessarily in the x direction, just in the direction of B. So we can go ahead and substitute this in, this vector B over magnitude of B in for our unit vector here. And we'll get a new equation for the projection of A onto B, and we can clean this up a little bit by saying the projection of A onto B is going to be equal to A dot B all over the magnitude of B squared times vector B, okay, the actual vector B here. Okay, so go ahead and make sure you have this down, this projection of A onto B formula, because we're going to be using this a lot. Okay, so jumping right into some examples. If we were asked to find the projection of U onto V, and then we want to write U as the sum of two orthogonal vectors, one of which is the projection of U onto V. Okay, so we've got vector U here, we've got vector V here. This is our terminal side. Okay, so this component here of U is going to be our projection of U onto V, right? This is going to be a component of U that is parallel with V. Okay, so first thing we need to do is find that projection of U onto V. And we can do that by using our formula here. And we really have everything we need already. Let's just go ahead and do U dot V. That's going to be 1 times 8 plus 2 times 5, all over the magnitude of V squared, which will be the square root squared, hint, hint, those will eventually go away, of 8 squared plus 5 squared. Again, all this times the vector v, which has components 8, 5. Okay, so we just need to go ahead and simplify this scalar here. Again, this is always just going to be some number. Okay, this is going to be a scalar value here multiplied by our vector. All right, so the projection of u onto v has the coordinate or the components 144 over 89 and 90 over 89. Okay, again, our square and our square root canceled out here, so we're just left with 89 in the denominator. And we got 18 times 8 for 144 and 5 times 18 for 90. All right, so that is the first part. Second part, let's find the sum of two, or let's write this as the sum of two orthogonal vectors for vector u. So our two orthogonal vectors will have the projection of u onto v, that's this vector here, and then our u2, that's actually going to be this vector right here, right? Because we want to create this sort of right triangle with u here as our hypotenuse, right? Okay, so if we solve this for u2, that's just going to be vector u minus the projection of u onto v. Now both of these are just vectors, right? And we know how to subtract vectors, especially in component form. That's just going to be 1 minus our 144 over 89 and 2 minus our 90 over 89, like so. And so u2 is going to be negative 55 over 89, 88 over 89. All right, so we're not quite done. We just found u2. Now we want to write u as the sum of two orthogonal vectors. Well, we have those two orthogonal vectors right here. So I just can go ahead and plug those in to this equation that we started out with. And that sum of two vectors looks just like this. Okay. All right, so our second example, it's going to be the same thing, but this time our directions are going to be opposite here for my projections. So this is what our vectors look like on our coordinate plane here. So we need to go ahead and find the projection of u onto v. Projection of u onto v. And notice that u is going the opposite direction as v, right? So let's think, how can I have a projection of u onto v? Well, keep in mind it just needs to be parallel with v. Okay, it doesn't need to be going in the same direction. So my projection of u onto v is actually going to be going the opposite way, the opposite direction. However, it'll still be parallel, right? Okay, so then this is going to be the projection of u onto v, this little vector right here, or this vector component of u. And then we can go ahead, again, we're just going to plug this into our equation. Okay, so we'll have negative 3 times 6 plus 4 times 1 all over 6 squared plus 1 squared times our vector v. And when we simplify, the projection of u onto v looks just like this. Okay, so that is the projection of u onto v. Now we just need to write u as the sum of two orthogonal vectors. So again, we're going to have u is equal to the projection of u onto v plus u2, and u2 is just going to be this vector component right here. That's u2. That's this sort of larger vector component right here. And again, we just need to find out what u2 is first. So that's going to be u minus our projection vector of u onto v, which we already found. So we can go ahead and do that vector operation. And when we write vector u as the sum of these two vectors, that looks just like this. All right, now let's get into calculating forces. We're going to get into some real-world applicability here for our vectors. We've got a boulder sitting on a mountain at an incline of 60 degrees. It is a 10,000-pound boulder. It is quite large. Ignoring the force of friction, we're just going to do this to make this a little bit simpler for us. What force is required to keep the boulder from rolling down the mountain? So first thing that I would recommend on this one is draw a picture. You guys know how great of an artist I am. So we've got this nice squiggly boulder here. We've got our mountainside here at 60 degrees. We've got the force of the boulder. That's going to be always coming straight down. All right, and then v here is just a unit vector that is in the direction of the mountainside here. Okay, I just want us to have that for reference. And then F1 will be the force in the direction of our mountainside again. That's trying to pull this boulder down. Okay, trying to pull it down the mountainside. So we need a force that is going to keep it up and keep it from falling down the mountainside. So our vector F, that's going to be 0, negative 10,000, okay, because that's 10,000 pounds, heading straight down. So our F1, okay, that is the component of F, and that is the projection of F onto V. Let's think of that as the projection of F onto V. So if I draw a little free body diagram here, say this is the point of our boulder here. Okay, we've got F coming straight down. V, again, it's not quite drawn to scale. V is just a unit vector in the direction of our mountainside. And F1 is the projection of F onto V. Okay, so we need to go ahead and find vector V, and that is going to have the magnitude of V times cosine theta and the magnitude of V times sine theta. But we know that theta is 60, and we know our magnitude is 1, again, because this is a unit vector. So cosine of 60 is going to be 1/2, and sine of 60 will be √3/2. Now, we need just to realize something, and that is this important point here. The force that is required to keep this boulder from falling is going to be the opposite of F1. All right, so whatever F1 is, that force is going to be the opposite of that. So it's going to be going this way, right? Opposite F1. That's what we have right here. Okay, so just keep that in mind as we are trying to solve for F1 and for this force keeping the boulder from rolling down. Okay, so we've got our important stuff here off to the side. Let's go ahead and find the projection of F onto V. Again, that is what F1 is, and when we can find that, then we'll be able to know our force here. So we have everything we need. We just got to plug in F dot V, and then our magnitude of V squared, and all that times vector V. And when we simplify what we have here for our scalar, we end up with negative 5,000 √3, okay, times vector V. Now, I'm not worried about this vector V, again, because this is just the unit vector in the direction of the mountain. Okay, so that just tells me that this force is going in the direction of the mountain. Okay, so the magnitude of this force is actually what we have here. All right, so this really is our force F1. That's the magnitude of our force F1, kind of. And so if we go ahead and take or find the opposite of this, right? This is negative 5,000 √3. So 5,000 √3 is going to be approximately 8,660 pounds, all right? So that's going to be the force heading up this way, keeping that boulder from falling. All right, so that is calculating a force. Now let's calculate work here, okay? So we got a person pushing a load. Now, what is work? All right, work is when we actually are moving something instead of just keeping something static. Now we're actually moving. We're moving something. So this person is pushing on some load, okay, and they're moving it from point A to point B. Now, if I take a closer look at this area right here, okay, we've got our force F, okay, that's the person pushing down at an angle because they are taller than this load. And then the projection of F onto this vector AB, because this is the distance that we're going here, okay, from A to B. That is actually a vector, right? And that's the distance that we're moving. Okay, that force is actually what moves our box here, or our load. Okay, and we have some certain angle that we're pushing on because right now we're not pushing directly into our load, we're pushing down at an angle. All right, so there's a couple ways we can calculate work. Okay, so we can multiply the magnitude of the projection of our force onto our AB vector, okay, our distance vector, and the magnitude of that distance vector itself, so magnitude of AB, or we can take the dot product of our force with AB. So F dot AB is another way. Both of these ways we can calculate our work. All right, so again, we have this situation here. A person is pushing a load, through, not up a room, but through a room that is 5 meters, okay? This person is using a force of 534 newtons and pushing down at an angle of 25 degrees from the horizontal. How much work in joules is this person doing? Okay, so our free body diagram shows this situation here. We've got our force being pushed downward at an angle of 25 degrees. So the projection of F onto AB is going to be the actual force that's moving us in the horizontal direction, okay? Because our box isn't going up or down at all, it's just going in the horizontal direction. And we're given the magnitude of that force here. So we're going to do this both ways. Okay, so work is going to be the projection of F onto AB, the magnitude of that times the magnitude AB. And the magnitude of AB we know is just 5. And the projection of our force onto AB, we can calculate that as the projection of our force, okay, times the cosine, or sorry, not the projection of our force, but the magnitude of our force times the cosine of theta, right? That's just using our right triangle trigonometry that we can kind of see here. Okay, so we can go ahead and calculate that to be approximately 484 newtons. And that times our 5 meters is going to give us a work of 2,419.842 Newton meters. Okay, now we have another unit for Newton meters. We actually call that a joule, so we would call that 2419 joules. Okay. Now let's do this the other method where our work is equal to the dot product of F and AB. So F dot AB. So F is going to be in component form. That's going to be the magnitude of F times cosine theta, magnitude of F times sine of theta, right? Okay, again, just using our right triangle trigonometry there. So what we have, we've got 534 cosine 25 and 534 sine of 25. That's going to be that one would be this, that vertical component would be this blue arrow right here. All right, in component form, AB is going to be 5, 0, because we're moving horizontally 5 meters. We are not moving vertically at all. All right, so the dot product here, we could say 5 times 534 cosine 25 degrees plus 0 times 534 sine 25 degrees. All right, and then this term here would go to 0, and we would be left again with 2419.842 joules. Okay, so both methods work in finding our work. All right, guys, that's all I have for this video. Good luck with your practice.